Hello. In explaining the example in the previous video, I forgot to mention one important implication of the omitted variable bias. You may interpret the omitted variable bias as a violation of the first assumption. So remember, in chapter 4, I introduced three important assumptions to have a causal interpretation. The first one is conditional mean zero assumption, and the second was the IID assumption, and the third was about the outliers. And the omitted variable bias is a bias. This problem arises because when there is an omitted variables, then the first assumption is violated. Let me show you how you can understand this. So suppose that the stock market, Y is the stock market, and Y is determined by the COVID cases, the number of COVID cases, and the government spending, and additional at a term. And suppose that this is how the stock market is determined, but you do not observe the government spending in the data, so you only use one variable X. And this is your model that you estimate, which is different from the correct model. In this case, because this is not observed, so this part, beta 2z, is absorbed into the error term in your model. So in your model, your error term has to take care of the original error term plus the omitted variable. And so your error term is actually this. This is your error term. And remember the first assumption was the conditional mean zero assumption, which can be written in this way. So regardless of the value of x, so x is the COVID cases, no matter what's the COVID cases is, number of COVID cases is, the error term must be on average zero. So there should be no pattern, there is no trend in the error term with respect to the regressor. However, it is violated if you replace the error term with this guy. So this is your virtual error term, including z. And then the problem here is higher COVID cases implies higher government spending. So that means if you replace the error term with beta 2z plus u, then this can be written in this way. Even if the original error term is okay, suppose that this is fine, it is zero. But the problem is here. It is not zero. So the expected value of the government spending increases as x increases. The point here is there is a trend. So what you want is you want the trend, there is no trend, and the expected value is the same for any possible x. But in this case, it is easily violated. So the government spending is expectedly higher when the COVID case increases. So therefore, now this is another way to interpret the problem associated with the omitted variable. And let's go back to the original lecture slide. So back to the student-teacher ratio example, we want to estimate beta 1. It is the causal effect on test scores of a change in the student-teacher ratio by 1. So when the student-teacher ratio changes by 1 unit, the test score changes by beta 1. And the first least squares assumption was this. You remember I mentioned it earlier. So, and the error term is the unobserved factors that you could not include in your regression model, but they have effect on the outcome. So influences y, but not included in the regression. So these are so simply the error term includes all the omitted variables. All the omitted variables are included in U. And then if the omitted variable has something to do with X, then you get this problem. This violates the first assumption of the least squares, and so the violation will cause a bias in your estimator. So it is overestimating or underestimating. So an example here, no, not an example, but so the omitted variable z must satisfy two conditions. As you can see earlier, the government spending is a determinant of the stock market. And the government spending is correlated with the COVID cases. In the student to teacher ratio example, the example is this. So English language ability. So some schools have more foreign students, foreign-born students, or students who speak a different language at home. So if you could observe the English language ability, average ability of the students, then let's think about this effect on y and its correlation with x. So obviously, if there are more students who are not native in English, then it will have a negative impact on the test scores. Of course, the tests are taken in English, so test scores will decrease if the English language ability decreases, if there are more foreign-born students. But at the same time, the higher, like the more foreign-born students imply less affluent communities or less affluent school districts. So immigrants are usually less affluent than like natives. So in this school district, the school budget it is likely that the school budgets are short and the student to teacher ratio would be higher. So then let's put it this way. The more foreign-born students cause a negative impact on Y. At the same time, the more foreign-born students, it implies higher student-to-teacher ratio. So this is positive correlation, and between Y and Z, it's a negative correlation. So these conditions are satisfied. Both are, so Z determines Y and Z is correlated with X. The direction, by the way, the sign is important. Then because if you could not observe this variable, hidden variable, confounding variable, then your estimate will be biased. What is the direction of the bias? Is it, if the bias is positive, that means you are overestimating the true parameter. If the bias is negative, you are underestimating the true parameter. How can we expect that? So let's think about this. Let me explain in casual words. So originally, like without the confounding variable, higher beta 1 is the effect of student to teacher ratio on the test score. So beta 1 must be negative. As the student teacher ratio increases, the test score will decrease. But at the same time now let's think about the indirect effect. The higher student teacher ratio, then that implies it is more likely to be less affluent school district, and that means there are more foreign-born students, and that implies lower test scores. Then in sum, so the indirect channel implies higher student to teacher ratio also causes drop in the test score through the indirect channel. So the direct channel is also negative, and indirect channel is negative too. Both channels are negative. Then you cannot distinguish them. You only observe, your data only tell you the total effect, and the total effect is even more negative than your true parameter you wanted. Just that's the common sense. That's my guess, and reasonable, educated guess, I think. So then, if my rationale is correct, then your estimate will underestimate, or your estimator will underestimate the true effect of student to teacher ratio, and the bias is negative. That's what I expect, and what you have to think about in this analysis. So it can be derived, mathematically derived. I will skip that. Skip that. So by the way, so this is worth mentioning. This is the bias because beta hat is what you estimate, and beta without hat, is the true value you want. So their difference is converging to something which is the bias. So what you want here is you want this to be 0. That was the consistency, and that means the estimation error will disappear in the limit. That's what we learned earlier, but now it's not 0 anymore. So that is the this value is the bias, omitted variable bias. And so this is the formula. You don't need to know this. And the intuition is the same as before. So you have to think about the indirect channel, how X affects Z and how Z affects Y. You have to think about the signs, and then you can guess the direction of the bias. So even if you cannot estimate the true parameter, but you can still guess where it lies. For example, if your estimator is minus 10, for example, if your beta 1 hat was minus 10, and if you know that you are underestimating the true parameter, then at least you can say that the effect of an increase, 1 unit increase in the student to teacher ratio will decrease the test scores by less than 10 points. Not exactly 10 points, but it should be less than that, considering the bias. But how, I don't know. No one knows how big the bias is. So that is another problem. And the solution is to include the omitted variable into the regression. Okay, I'm going to continue in the next video. So thank you for watching.